Hello, my name is Kavitha and my paper is titled Maximum Matchings and Popularity. Our input here is a bipartite graph where every vertex has a strict ranking of its neighbors. As in this example here, the numbers on edges denote these ranks. This is a very well-studied model in two-sided matching markets, and such a graph is also called a marriage instance. This is used in many real-world applications, such as matching students to schools and colleges, and medical residents to hospitals, and so on. What one typically seeks here is a stable matching. A matching is stable if there is no edge that blocks it. An edge AB is said to block a matching if both A and B prefer each other to the respective assignments in M. So in this example, the blue matching is stable. Gale and Shapley, around 60 years ago, showed that stable matchings always exist in a marriage instance, and their algorithm finds one in linear time. There could be exponentially many stable matchings in a marriage instance. However, all of them have the same size, and a stable matching need not have maximum size. In this example, there is a size 3 matching. However, it's not stable. There are many applications where the size of the matching is of primary importance. That is, the size is more important than vertex preferences. Such applications include matching doctors to hospitals in a pandemic, assigning sailors to billets, and the school placement problem. In all these applications, the set of admissible solutions is the set of maximum matchings. And among all maximum matchings, we seek a best one. So how do we define a best maximum matching as per vertex preferences? A natural extension of stability is to ask for a maximum matching with the least number of blocking edges. However, this problem is NP-hard. So let us look at another natural relaxation of stability. So this is the notion of popularity. Any pair of matchings can be compared by holding an election between them where vertices are voters. So let's ask every vertex to vote for one matching or the other, or abstain from casting its vote. And let's count the number of vertices that prefer one matching to the other. So let's hold an election between the red and blue matchings. So the two middle vertices prefer the red matching because they get assigned better partners in the red matching. The two bottom vertices prefer the blue matching, and the top two vertices abstain from voting because they get assigned the same partners in both the red and blue matchings. So this election between the red and blue matchings is a tie. It's 2 versus 2. Let's hold an election between the red and green matchings. So it's easy to check. There are 4 vertices that vote for the red matching and only 2 that vote for the green matching. So the green matching loses this election. A popular matching is one that does not lose any election. So if M is popular, then M is at least as good as any matching, where the at least as good as relation is defined above. So M is at least as good as M prime if the number of vertices that vote for M is at least the number that vote for M prime. So Garten Force in 1975 introduced this notion of popularity, where he observed that every stable matching is popular. So popular matchings always exist in a marriage instance, and one such matching can be computed in linear time by the Gale-Shapley algorithm. However, even the notion of popularity does not capture what we seek, because it could be the case that no maximum matching is popular. As in this example, there is a lone maximum matching here, the red matching, and it loses to the size 2 blue matching. So 4 vertices vote for the blue matching and only 2 vote for the red matching. So rather than ask for popularity in the entire set of matchings, since we're interested only in maximum matchings, why not ask for a matching that's popular, restricted to the set of maximum matchings? That is, we want a matching that does not lose to any maximum matching. We want a maximum matching that does not lose to any maximum matching. Let's call such a matching a popular max matching. So if M is a popular max matching, then M is at least as good as M prime for any maximum matching M prime. So M could lose an election against a non-maximum matching, but we already declared that non-maximum matchings are not interesting to us. So those elections are irrelevant for us. So does a popular max matching always exist in a marriage instance? So we considered this question a few years ago and showed that yes, popular max matchings always exist in any marriage instance, and one such matching can be computed in polynomial time. So let's ask a tougher question here. Suppose there is a cost function on the edge set, and we're not happy with any popular max matching. What we seek is an optimal popular max matching, that is a min cost popular max matching. Is it easy to find one? The min-cost stable matching problem is a very well-studied problem, and there are many polynomial time algorithms known to compute such a matching. Several of them optimize over the stable matching polytope that has an elegant linear size description. In contrast, finding a min-cost popular matching in a marriage instance is NP hard, and the popular matching polytope has near exponential extension complexity. Surprisingly, a min-cost popular max matching can be computed in polynomial time, and the popular max matching polytope has a compact extended formulation. So finding an optimal popular max matching turns out to be easier than finding an optimal popular matching. So let's revisit this algorithm from a few years ago that finds a popular max matching. This algorithm is an extension of the Gale-Shapley algorithm in the given instance G. Rather than run this extension of Gale-Shapley algorithm in G, this could equivalently be viewed as running the Gale-Shapley algorithm in a new instance G star. And the advantage of this point of view is it allows us to show every stable matching in G star maps to a popular max matching in G. So our main technical result is that this mapping is surjective. That is, every popular max matching in G is the image of a stable matching in G star. So finding a min-cost stable matching in G star solves our problem. So that would map to a min-cost popular max matching in G. What is this instance G star? Roughly speaking, it is made up of n copies of G. In more detail, for any vertex A in capital A, the set A star has n copies. So though there are n copies of A, we want at most one of them to be matched to a real neighbor. So let's also introduce n-1 dummy vertices corresponding to A, and we will set up preferences such that n-1 copies of A have to be matched to these n-1 dummy vertices in any stable matching in G star. So that will ensure that only one copy of A can be matched to a non-dummy neighbor in any stable matching in G star. So the set B is also a subset of B star. For any edge in E, there will be n edges in E star. Every dummy vertex has degree exactly 2. DIA will be adjacent to AI-1 and AI, and it prefers AI-1 to AI. The preferences of other vertices are as follows. If A's preference order in G is as given here, then A0's preference order in G star is exactly the same, only we append a dummy vertex as its worst choice neighbor. And for all the other copies of A, we'll be attaching a dummy vertex at the start and a dummy vertex at the end of its preference list. But the real preference list, other than the dummy vertices, is the same as A's preference order in G. Yeah, and for AN-1, the preference order starts with a dummy vertex, and it's the rest of it is the same as A's preference order. So the preference orders of vertices in B star, that's important for us. So if B's preference order in G is as given here, then B's preference order in G star is all its subscript n-1 neighbors at the top of the list, followed by all subscript n-2 neighbors next, and so on and so forth. And finally, at the very end, we have all subscript 0 neighbors. Within all subscript n-1 neighbors, it's as per its original preference order in G. Similarly, within all subscript I neighbors, it is as per its original preference order in G. Let S be any stable matching in G star, and let S prime be the corresponding matching in G. So S prime is obtained by deleting all edges incident to dummy vertices and replacing any edge AIB with the original edge AB. So we claim that S prime is a matching in G. That is thanks to the dummy vertices. We ensured that at most one vertex among all copies of A is matched to a neighboring B. So it would be the case that S prime is a matching in G. What is non-trivial is that S prime is a popular max matching in G. In order to show this, it will be useful to partition A into n sets as given here. AI would be the set of all those A's whose ith copy is matched to a non-dummy neighbor in S. So we can view all these sets A0 to AN-1 as given here. Similarly, we'll partition B into n sets where Bi is the set of all those B's matched to a level I or a subscript I neighbor in the matching S. So S need not be a perfect matching. There could be vertices left unmatched. The left out vertices in A are added to the topmost set AN-1, and the left out vertices in B are added to the bottommost set B0. The matching S prime has nice structure. It respects levels, that is due to the definition of the sets Bi, and we can show it is a maximum matching in G. S prime need not be stable, but any blocking edge to S prime has to go from southwest to northeast, as shown here. The red edges are blocking edges to S prime. So all these properties enable us to show that S prime is a popular max matching in G. This is a very rough sketch. I refer you to the paper for all the missing details. So let's spend some time on proving the main theorem. That is, this map from the stable matchings in G star to popular max matchings in G is surjective. So given a popular max matching M in G, we want to come up with a stable matching M star in G star such that M is the image of M star. So for any edge AB in M, we need to come up with a level or a subscript I so that AIB is an edge in M star. So it will be useful to think of the subscripts as levels. And so we need to find the right level to place this edge AB so that when we look at the corresponding matching in G star corresponding to this leveled view of M, what we get is a stable matching in G star. We'll take the help of LP duality here in coming up with these levels. As an easy case, suppose G admits a perfect matching. So M is a perfect matching in G. Let's define this edge weight function weight subscript M. So for any edge AB, weight of AB under this edge weight function is the sum of the votes of the endpoints of the edge for each other relative to their assignments in M. So if the edge blocks M, the edge weight is 2. If both A and B prefer their assignments in M to each other, then the edge weight is -2, otherwise it is 0. So it follows from the definition of this edge weight function that for any perfect matching N, its weight under this edge weight function is the difference between the number of vertices that prefer N and the number that prefer M. So if M is a popular perfect matching, then for any perfect matching N, its weight under this edge weight function is less than or equal to 0. The weight of M under this edge weight function is exactly equal to 0 because every edge has weight 0 under this edge weight function. So M would be an optimal solution to this linear program, which is the max weight perfect matching LP. The dual LP will be very useful to us. The dual LP is here. It's very simple. So it just has these covering constraints. So if M is a popular perfect matching, then there exists a dual feasible solution whose objective function value is 0. So the constraint matrix here is totally unimodular. There's always an integral optimal solution. In fact, it's easy to show the following lemma, that there exists an optimal solution to the dual LP with a lot of structure. So the alpha values of all vertices in A are in the set 0, -2, -4, so on. And the alpha values of all vertices in B are in the set 0, 2, 4, so on. So this lemma can be shown using complementary slackness and our edge weight function. That is, every edge weight is in +2, -2, 0. So let's use this optimal dual solution. We call this a dual certificate for our popular max matching M. So let's use these alpha values as follows. Let's define the matching M star to be. So let's use alpha value of A to define the subscript of A. So if alpha A is -2i, then the subscript of A will be I. So M star is a collection of all these edges AIP, where I is basically coming from the alpha value of A. And we also need to add necessary edges incident to dummy vertices. These are as given here. If A's alpha value is -2i, then all AJ, where J is strictly smaller than I, are matched to their worst choice neighbors. And AJ, where J is strictly larger than I, are matched to their top choice neighbors. So recall these preferences from what we discussed earlier. So it's a simple observation that M star is a perfect matching in G star. What is non-trivial is that M star is stable. How do we show this? So suppose A's alpha value is -2i, then AIB is an M star. And we also said that AJ for J strictly larger than I, all these vertices are matched to their top choice neighbors. Hence, there is no blocking edge incident to any of these vertices. So what we need to prove now is there is no blocking edge incident to the remaining copies of A also, that is from A0 till AI. So let's look at any neighbor W of A. The edge covering constraint allows us to show that alpha value of W is at least twice I minus 1. So W is matched to a level J neighbor where J is at least I minus 1. So this immediately implies there is no blocking edge between W and any of A0 till AI minus 2. But that's by W's preference order in G star. Recall that W prefers any higher level neighbor to lower level neighbor. So using the same edge covering constraint, we can also show there is no blocking edge between W and either AI minus 1 or AI. It's quite easy to show this. So let's look at the general case now. G need not have a perfect matching. So let M be a popular max matching in G. And let's look at the subgraph induced on vertices matched in G. So let's delete all vertices left unmatched in M and look at the subgraph induced on the remaining set of vertices. So M is a popular perfect matching in the subgraph. So M is an optimal solution to the above LP. This is the max weight perfect matching LP. So we're familiar with this LP. We're familiar with its dual LP also. And we also know that there is an optimal solution to this dual LP with these nice properties. And then we show one more very important property, that the alpha values of neighbors of unmatched vertices take the highest possible values in the allowed sets. That is, if A is a neighbor of an unmatched vertex in B, then A's alpha value is 0. And if B is a neighbor of an unmatched vertex in A, then B's alpha value is twice n minus 1. And these properties, the first two properties, which are old properties, and the later property, which consists of two new properties, these will allow us to show that M star is stable in G star. So the matching M star is exactly defined as we did before. So we use the alpha value of A to define the subscript. And the edges incident to dummy vertices are exactly as before. All the vertices AJ, where J strictly smaller than I, are matched to their worst choice neighbors, and all the vertices AJ, where J strictly larger than I, are matched to their top choice neighbors. And for vertices A left unmatched in M, all the vertices A0 till AN minus 2 are matched to their worst choice neighbors, and AN minus 1 is left unmatched. And we claim M star is a stable matching with G star. So let's consider any edge AJW that arises out of an edge that belongs to the subgraph G prime. It follows exactly from our previous analysis that this edge AJW does not block M star. So what we need to focus on are the edges that are missing in G prime. So each of these edges has an unmatched vertex as an endpoint. So let us look at one such edge AW and let A be unmatched in M. So we know from one of our new properties that the alpha value of W is twice n minus 1. So W is matched to a level n minus 1 neighbor that it prefers to A. Hence the edge A n minus 1 W does not block M star. Also, none of these other edges blocks M star, and that is by W's preference order in G star, because it prefers a level n minus 1 neighbor to any lower level neighbor. So now let's look at an edge AW where W is left unmatched in M. So again, by our new property, alpha value of A is 0. So A0B is in the matching M star, and B is the neighbor that A prefers to W. So the edge A0W does not block M star. And all these vertices A1 to AN minus 1 are matched to the respective top choice neighbors. Hence, none of A1W till AN minus 1W, none of them can block M. Hence, M star is stable in G star. So let's sketch a proof of the lemma that was crucial for this proof. So we already know there is an optimal solution to the dual LP that satisfies these two properties. What we want to show are these two new properties. So let's call these two new properties property 1 and property 2. Suppose alpha does not satisfy property 1. Then let us update alpha. Let us force alpha A and alpha M of A to be 0 for every vertex A that has an unmatched vertex as its neighbor. Similarly, if alpha does not satisfy 2, then let us update alpha B to be twice n minus 1 and alpha M of B to be minus 2 times n minus 1 for every B that has an unmatched vertex in A as its neighbor. So forcing alpha values like this is going to violate feasibility. And so alpha may stop being a feasible solution to the dual LP. There might be an edge that's no longer covered. So we will run some update rules to make alpha feasible again. These are very natural rules that correspond to vertices in B that move to lower levels, dragging their neighbors and partners of these neighbors to lower levels. And similarly, vertices in A that have moved to higher levels pull their neighbors and partners of their neighbors to higher levels. And these vertices that have moved to lower levels or higher levels in turn pull their neighbors and partners of these neighbors to higher, lower, whatever the corresponding level. And this process continues. For us to show this process terminates, we need to show that no vertex gets pulled both upwards and downwards. Then this process would never end. And indeed, no vertex gets pulled both upwards and downwards. And that is because there is no augmenting path with respect to M. We show that if there was a vertex that gets pulled both upwards and downwards, then we can construct an augmenting path with respect to M. However, M is a maximum matching, and so an augmenting path is forbidden. So this allows us to show our update routine does terminate, and so get a desired dual certificate alpha. We also have a hardness result here that is on Pareto optimal matchings. A matching is Pareto optimal if there is no matching where no vertex is worse off and at least one vertex is better off. So finding a Pareto optimal matching is easy. Any stable matching is Pareto optimal. So we consider the problem of finding a min cost Pareto optimal matching, and we show that's NP hard. And this hardness also extends to finding a min cost Pareto optimal max matching in a marriage instance. Thank you.